In this video, I'll talk about two important groups in physics, the Galilean group and the Lorentz group. So in physics, we want to make sure the physics law is the same across different frames. So let's draw out two frames. One corresponds to a standing guy. Let's call this the S frame. And the coordinate of this frame will be the X and Y. Now, there's another guy running. And there's also a frame attached to him. Here I'm using dashed line because I want to focus on what the S frame sees. And this guy is running with speed v. And in the other drawing, I want to focus on what the S prime coordinate is seeing. So I will do the dashed line for the S frame for the standing person. And then I use solid line for the running person with the prime frame and X prime, Y prime. So in the point of view of the running person, the S frame is going backward with speed v. Now, let's say something physical happened, an event, a light bulb. Let's say a light bulb blinked, and this thing is physical. We don't need frame to make it happen. The light bulb just blinked by itself. But to describe this blink, we need some coordinate. If we are the standing guy will say this light bulb blink at some time t, coordinate x and coordinate y. And for the prime frame, the running guy will think that this light bulb blink at some time t prime, position x prime and y prime. Now, if we want to write down physics law that is the same across different frames, we want to find some quantity that is the same across different frames. Our everyday experience tells us that a quantity called acceleration is the same in these two frames, which means the second time derivative of x with respect to t is the same as the second derivative of x prime with respect to dt prime. Same with the y position. But we know that this is not true. Special relativity tells us that the acceleration is not actually the same across these two frames, but the space-time interval, which is defined as the change of time square minus the change of position square, is actually the same across these two frames. Now, remember that we say if you have something that is unchanged under some action, then you can define a group. Here, the thing that is unchanged is acceleration or the space-time interval, and then the action is going from one frame to another frame. So, in old days, when we think that acceleration is the same, we can define a group that is all the actions, all this frame transformation that keeps the acceleration the same across different frames. Those transformations are the familiar time in the prime frame is the same as the time in the prime frame, and the position in the prime frame just gets shifted by the speed times the time. This transformation together forms the group called Galilean group. So we can define Galilean group as the frame transformation that keeps the acceleration unchanged. Now, on the other hand, if we realize the thing that is unchanged is actually the space-time interval, we can define all the transformations that do that, which is the familiar Lorentz transformation. The time in the prime frame is a factor of gamma, that of a prime frame, and some factor of position, and the position will also be affected by a factor of gamma. So the group that we define in this way by all the frame transformation that keeps the space-time interval unchanged is called the Lorentz group. These groups are big. There are infinite amount of different transformations you can do, no matter which group you are looking at, but all of this defines the group elements inside these two different groups. So we see, because in physics we want to define things in a symmetric way, naturally we are defining a group under what theory we are doing. Now, in this case, special relativity is just saying that our universe is a representation of the Lorentz group. Not the Galilean group. That's all special relativity is about. You see, one of our greatest achievements in modern physics is finding the underlying group of the symmetry of our universe. Now, in the next video, I would go more about how our universe represents this underlying Lorentz group.